So now this is a long example. There'll be lots of writing. Probably should pause it. Ruben has a lousy car. There's a 40% probability that the steering will fail. There's a 30% probability that the brakes and the steering will both fail at the same time. And in a moment of horror, Ruben realizes that the steering has failed. And so the question is, what's the probability that the brakes have failed as well? So the steering has failed. When he goes to pump the brakes, are we going to have an epic disaster? So we're going to define there's two events here. So the first event is going to be that the steering fails. And the second event is going to be that the brakes fail. So what do we have? There's a 40% probability that the steering will fail. Okay, so the probability of the steering failing is 40%. There's a 30% probability that the brakes and the steering will fail at the same time. So the probability of steering and brakes failing is 0.3. And then the question is, so the steering, in a moment of horror, Ruben realizes that the steering has failed. What's the probability that the brakes have failed? And so the question is asking, it's saying, what is the probability that the brakes have failed given that the steering has failed? So we have a formula, and the formula is over here. So it's actually kind of pretty straightforward if you have the formula. So the probability of B given A is the probability of them both happening divided by the probability of that happening, which in this case is 0.3 divided by 0.4, which is 75%. So in this situation, if the steering has failed, there's actually a 75% probability that the brakes have failed as well. I could show this in a different way. I've kind of preset up if we're going to do our weighted tree diagram, so the probability that the steering failed was 40%. And the probability that the steering is okay, 60%, but that's not really going to matter too much. Now what we know is that, oops, where did it go? That's the next example. We know that there's a 30% probability that both the brakes and the steering will fail. Now that's not this over here. The 0.3 is actually over here. It's the probability of this and this happening. And we're trying to find out what this is. So let's say we call that x, so it'd be this times x is 0.3, so it's going to be, and none of these really matter, because if the steering's okay, we know that the steering has failed. So we don't actually care about this part of the tree. And I don't actually care about the probability of the brakes being okay. I want to know the probability of the brakes failing. So we're really, in this problem, we're kind of zooming in on this part of the situation. So what we're saying is 0.4 times the probability of the brakes failing given that the steering has failed is equal to 0.3. And if I rearrange it, it's going to be, this doesn't really matter as well. If we rearrange it, we're going to get what we got before, the 0.3 on the 0.4. There's some pretty vomity colors here, right? Which is going to be 75%, which means that this number, if the steering fails, there has to be a 75% that the brakes fail in order for them both to go at the same time. Not that it matters, but it turns out there would have been a 25% chance that the brakes were okay, which is the same answer we got before. So you could either do it with a formula, or you could reason out like this. Both of them are acceptable. fit in the last example. You have a full deck of cards, 52 cards in a deck. You take 32 of them without looking, and you throw them into the fire, and they burn. And now you only have 20 cards left. So you're a stack of 20 cards, and the question is, what's the probability that the top card will be the Queen of Spades? Now, it might be tempting to say that the answer is 1 in 20, but it's not, right? So what we want is we want the probability of being the queen. So we have, now in order for it to be the queen, what has to happen is that there's two events that have to happen. Maybe I shouldn't use A and B. I'm going to use A and B. So A is going to be that the Queen of Spades must not burn, and event B is that you pick the Queen of Spades, or the Queen of Spades is the one on top. So let's figure out the probabilities of that. So both of these in order to pick the Queen of Spades, both of these things have to happen. I have to not pick the Queen of Spades, and I have to not burn the Queen of Spades, and then I have to pick it from the 20 that are left. So if I was going to do that, the probability of A, the probability of not burning the Queen of Spades, so there was 20 of them that we didn't burn, is going to be 20 out of 52. And the probability of picking the queen, given that I did not burn anything, is going to be 1 out of 20, which means the probability of both of them happening is going to be the probability of A times the probability of B minus A, B given A, which is going to be 20 out of 52 times 1 over 20, which is 1 out of 52. Which kind of makes sense. What this means is that burning the cards actually didn't do a thing. Right? There's a 1 in 52 chance that if you have a deck of cards and you pick a card off the top, the probability of it being the Queen of Spades is 1 in 52. If you burn 32 cards, the probability that the top card is the Queen of Spades is still 1 out of 52. And that's it.